then let's start today's lecture. So what we have seen that in the previous class, that for any population growth model we need this quantity. We have to write from the assumptions, that assumptions are based on the basic observations from the natures. Now based on those observations, we generally write the per capita growth rate, that 1 by n and dn dt, where n is the population size at time t. Now we have seen the unlimited growth model, where we have assumed that there are a lot of resources available, and those resources are vital for living beings. Means the populations we are studying, that resource is very essential for that populations. Now if that resource is infinite, then there is no limit that how much individual can use that resource. So then naturally all the individuals will use that resource, and they will grow at a constant rate per capita. On average, every individual's reproduction rate minus death rate minus birth rate will remain equal. So if that is the case, then we have seen that the population's size at time t can be expressed in terms of population size at time t equal to 0 in this fashion, and it is called, since from our zeroth time or from our old state of the population we can predict our population size for any time. So this is the prediction formula, and it can be written in closed form. Closed form means basically we can write in very simply. So it is showing that populations is growing at a exponential rate. So it will look like, so from, if it start in 0, it will increase and it will continue to increase like that. Now one thing I want to say here, that I want to so this is the now n at time t, and this is the time axis, this is 0 and this goes on. Now is this graph is showing this property or not? So from the equation, so we know that dn dt equal to rn. Does this graph is showing this property or not? To see that, we have to calculate the slope of this graph. Now let me tell you, or let me recall what the graph is from our mathematical class. So suppose there is a point in the graph, and if I draw a tangent, that means if I draw a straight line which only touches this curve in this point, then it is called the tangent of the graph. Now if that is the tangent, if now suppose that this tangent, that line which only touches this blue curve in a point, in this red point, suppose only this red point, then it is called the tangent. Now suppose this tangent makes an angle theta with this t axis, and then it is obvious that if I draw a straight line, parallel line to the t, these angles also will be theta. Now this means, now if I draw a very small segment, suppose this around here, so this angle will be theta. Now since this is dt and the increment in dt time is dn, so you can think like that dn dt actually the dn dt is the slope of this curve, or the slope of this curve at the point, at the red point. Now this curve, if you see that this curve is always maintaining same uh, same tangent, so dn dt equal to Rn. You can see that as n is increasing, so dn dt means the rate of change of the increase in the populations, that is the slope, that is equivalently, that is from the mathematical equation. And you can see this mathematical equation that its slope is, rate is changing, changing proportional to n. You can see also this from the graph also. You can see here, you can see when n equal to 0, when n equal to 0, what will be the dn dt? Dn dt should be 0. So n equal to 0, if you draw a line here, if you draw a tangent here, you see this tangent is parallel to this t axis. And if it is parallel, that means what angle it makes? It makes angle 0 degree. And what is the tan? Okay, so tan 0 degree means tan of 0 degree, tan 0 means 0. So that means it is, this graph is showing correct correct thing. This graph actually follows these equations. So at 0, its tangent is 0, and if we go to infinity, so it will look like this. So then tangent will become like that, and tangent, if that makes angle 90 degree. Okay, so let me stop my video, then it will be maybe video is stopped. I think, I don't know why it is stopped. Okay, yeah, now I have stopped my video, so maybe, but I can't see anything. That's the problem. Okay. Hi Subhusachi, are you there in the meeting, or okay, maybe, I don't know. Yeah, okay, well, let me start then. Now here it is basically, don't worry, this is basically another way of seeing that this curve is actually following these equations. So that is a way to draw a curve with only seeing the equations. So, and as you see, as n equal to infinity, the dn dt will become infinity. And when, what will be the tangent of the infinity? So the so it will become 90 degree angle with these t axis. So then also the tan theta, or the tangent, will become infinity. So that's all. Now let's move towards our limited growth model. So uh, this is a model which says that resource is infinite and population size is going to up to infinity. But in practice, it is we have seen that huh, I am not audible. Okay, uh, I'm okay. Let me. Now you can hear me, right? Ah, ah, maybe it's network. Oh, yeah. Then it is fine. Let's start now then. So, limited. Yeah. Now, limited growth model. So, where I was I? Yeah. So, in practice, the all populations is means the resource the population any population use, that is limited, that we have seen in nature. So as for case of human population, suppose that the crops the human farm, that is only support a such suppose a maximum number of individuals, a maximum number of human adult individuals, suppose that number is k. So k basically says the limit of the resource. So suppose we can farm such amount of resource, such amount of crop that can only sustain life of the k individual. So k is called the carrying capacity of the resource. So capacity of the resource. And in case of this other model, the carrying capacity was infinity. Now there is a carrying capacity, the resource cannot sustain as many individual as we want, but it suppose that if what will happen if suppose my population size n become k at some point of time, then what will happen then? So then the resource available to them is only enough for sustaining them. Now if some newborns are some new individuals born into that population, those individuals also need the resource. Now since the resource cannot go further, if we will not have much more resource than that. So that means if we want to allocate some amount of resource towards the new individuals, we have to abstain the older individual to use them. Now if it is happen so, then some older individual if not use that resource, means if some since this resource is very vital for that populations, so if some individual suppose small n number of individual born at that point of time, if we want to allocate resources towards these small n number of individuals, then we have to shift the resource from some other n number of older individuals. So we have to shift the resource from, yeah, yeah, yeah. Oh, you are not also okay, okay. Thank you, thank you. Yeah. Now you can see me, I think. See my screen as well, right? So yeah. So now we have to allocate resource from the older individuals to the new individuals. Now if I allocate the resource from older individual to the new individuals, then these individual will die. Now if this individual will die, and and the same amount of individuals for the new individuals, same amount for the new born individuals, then we can say that this nt old equal to this newborn individuals. So that means at that point of time the number of individuals die in the population will be equal to the number of individuals which who will born at that time, at that point of time. So what this says, so as we have from the started of this modeling series, so we learned that to make a mathematical model we need an assumptions, right? Some assumptions, we need some assumptions, some assumptions. Now we want to build some assumptions from our sense that if the population reach to the carrying capacity, what will happen then? So as it seems that in the if the population reaches to the k, that the change in the population with time will be stopped. That means that rate of change, what rate of change means, d and dt will become 0. So this is our first assumption. So d and dt will become 0. This is our first assumption at n equal to k. Now this assumption is first introduced by Verhulst at 1844, and if I can recall correctly, then at this point of time, means around this time, the another mathematician Poincare also dealing with the problem of the stability of three body problem, that means stability of the solar system, and the chaos was born at that time mathematically. So that is the thing. Now he introduced that in the population growth model, that population cannot grow infinitely, there is a limiting factor of the resource, and that limiting factor is incorporated by the carrying capacity. And he introduced the assumptions that when the population will reach at that limit, that carrying capacity n equal to when become k, then the rate of change in the population should become 0, because in that point of time no resource available, so population cannot grow further, so the growth will stop there. Now another assumption is what? So we required another assumptions, assumption number 2. So this is number 1 assumptions and assumption number 2. Now what will happen when for the people there is available the resource is available, the abundance of resource is there. When it will happen? It will happen when the number of individual in the populations is close to 0. It is very, if nt is very small, suppose at the initial phase or at any point of time the number of individuals in the populations is very small, and if the number of individuals are very small, so for them the resource will be enough to grow. Now then what will follow then? So that means when near to n equal to 0, what the dndt will look like, same as the infinite growth model, because here also the for the individuals, individuals, the resource was enough for that those individuals. So it should be a logical assumptions that at near n equal to 0, our dn dt means the rate of change of the population size should look like n. So they are growing at a constant rate, or they are growing at a constant rate of growth when it is very small, because the resource is available. So these are the two assumptions. So near, so dn dt should equal to Rn, or maybe write it in this version. So it's approach to Rn, limit n tends to 0, then it will become Rn. So this is the second assumption. So when n is approaching to 0, then the rate of change in the population should proportional to is a constant proportional to R. And if n number of individuals is there, and if all the individuals will reproduce at a rate here, so at the end of the time, so total number of individuals rate at which they are increasing, that is Rn. Now a simple equations uh, which satisfied both of these assumptions, that means dn dt is 0 at n equal to k, and dn dt is proportional to Rn when n tends to 0, is equation, is this equation. So let me write this equation. This is called the logistic equations that you are pointing out in the previous class, that there is a logistic equations and the exponential growth model. So this is the logistic equations. So this is basically 1 by n dn dt equal to r 1 minus n by k. Now let's check that at n equal to k whether dn dt is 0 or not. So if I put n equal to k here, so if I put n equal to k here, you will see that dn dt will become 0, since this, if I put n equal to k, so this part will become 0, so the first assumption is satisfied. Now let's see whether it's satisfies second assumption or not. So 1 by n dn dt limit n tends to 0, it will become limit n tends to 0 r 1 minus n by k. Now this r limit n tends to 0 1 minus n by k. So in this, when n goes to 0, so this term will become 0, this term will become 0, and only 1 remains, so this is r. So as it seems that at when the limit n tends to 0, so this 1 by n dn dt follows this form also. So that means this equation follows the above two assumptions. Now, so from our previous class we know that if we can mathematically write a equation, okay, maybe my, I don't know how my network, the status of the network is very low, so I don't know how much I can go with this network. So let's see. So here, where I was, okay, 1 by n dn dt, okay, that's. So as we learned from our previous class, that let me recharge my sorry for this interruptions, but let me recharge, then maybe I can, it will require 2 minutes. Okay. Yeah, I am apologizing for these things, that my network is not very poor. So let me restart from here. That is so where was I? 1 by n, dn dt is r by n. Okay. So as we have seen that our assumptions, we should mathematize our assumptions in a way that it will give the prediction. So we are successful to write a mathematical model from assumptions, and so that is 1 by n dn dt r by n. Now it to solve this, it's required a quite bit skill in solving integration, mathematical calculus, but as we know that many of our yeah, okay, let me, yeah, I'm very sorry for that, because my internet is not going very well. So okay. Let me see if I can. Yeah. So basically, no. So yeah, we have successfully written it down. Now to solve this equation, we need a trick in solving in mathematical calculus. But as we know that many of us, we are not very skillful at solving these type of equations. So I am writing these equations. So it will be your homework. If you want to that to solve these equations, you can solve. You can write a closed form solution. So that will look like nt will be, so n at t. So this is my prediction. So n at t will be the carrying capacity k by 1 plus k by n0 minus 1 e to the power minus rt. If I draw a graph, so it will look like with time time. So this is t, this is n. Now what we know from here, so from these equations, so for at n equal to 0, if I put n equal to 0, what will be the dn dt? dn, since n equal to 0, so if I take the n from this side to that side, so obviously dn dt will become 0. So that means at near about n equal to 0, it should be like this, and then when n is small, then dn dt should look like this, means growth should look like this as our previous case, because when n is very small, then we can neglect this term and dn dt will exactly look same as for previous case. So it should look like from here to exactly like here, but after some point when n become high, so again dn dt should become 0 at n equal to k. Suppose there is n equal to k, so it should look like at some point it will again become like this. So if I draw correctly, so it will look like this. Maybe I don't know whether this class is Airtel. Which one? Okay. So, I think it is. What is okay? Yeah. Nothing. So I think yeah. Become yeah. Now I think you can hear me, but uh, it seems it become horrible today, for me at least. Then for this because of this network issue. Let's see where can we go. Let me check whether my Airtel pack is there. I don't know why it is not showing. Let's see. Yeah, at least. Yeah, Subbusachi, can you see my? Can you hear and see my screen? Right? I hope so. You can see. Yeah. Thank you for your consideration. So here, okay. So that's how we draw this curve for nt with time t, as we seen that at n equal to 0 this dn dt you at if you put n equal to 0, so it will become 0, so you can see that it is parallel to this t line. Now again it will become 0 at when at k equal to n equal to k, so if n equal to k then also it become horizontal, and in between this it will follow dn dt equal to Rn. So exponential growth. So in between you can see that it is exponentially growing, then it is becoming a constant. So that's a way to visualize that equations, which is one way. Now, if you ask me, is there any other method to see whether or not the where this where is the final state of these equations, means at least where the size of the population, where will it reach? Now, yes, there is a possible way, and we will see it in further details in next in the in suppose in some in classes, because that's a topic of that class, that how you can analyze stability of a dynamical system. Now let me show you a glimpse of that by using these equations. So you see that this dn dt, if I write here again, dn dt is Rn 1 minus n by k. Now you see this dn dt always changing, this n is always increasing or decreasing with respect to time. Now where this dn dt will stop? Now at some point this dn dt should if the question is, if this dn dt will go towards the state where that dn dt will not increase further, that means n, can we find a state where n will not change further? That means that is it will remain in that state forever. Yes, we can we can say that yes, there is at least two such state where if the system reaches to the state where this dn dt will become 0. Now Subbujaji, can you tell me where this dn dt from this, by looking this equation, where the dn dt will become 0, that means n will not increase or decrease further. What is the value of those two n? Yeah. Right. Yeah. So this makes sense. N equal to 0 actually makes sense. Now both are, you are right, both are correct. So these two is called the stationary state, or called in terms of fixed point. Means if population reach to this point, the population will remain there forever, because for n equal to 0 it is obvious, if no one is there remain to reproduce, so that will be the state. So there will be no any individual to reproduce. So the population, you cannot see any other populations from out of nothing. So this is called the fixed point of these dynamical equations, or fixed state. Now among these, which is the stable fixed state? Means if I start from any initial condition, condition where the population will go, either it will go n equal to k or n equal to 0, because if they reaches to that point, it will stay there forever. Now to the trick is, suppose you start from very neighborhood of these 2 points. Suppose we start from neighborhood of very 0, so n equal to, suppose 0 plus epsilon. So epsilon is very small. Now put it here in this equation. So epsilon is tending to 0, it is very small number. So if I put it in this equation, it will become d, n means here epsilon, so n is epsilon, so d epsilon dt will be r epsilon 1 minus epsilon by k. Now you see epsilon is tending to 0, so 1 will be much greater than epsilon by k. So this epsilon by k will contribute means very less to this equation, so we can write d epsilon dt at the neighborhood of 0 is d epsilon. So you can understand that in the neighborhood, suppose it is the point 0, so in the neighborhood of 0, suppose only one dimensional equations, so write it in this way. So this is the, so suppose n equal to 0, so only in the neighborhood, suppose in this point, this is epsilon. So how this will change? It will change, the epsilon dt is proportional to r epsilon, and if we solve this equation, we will get the epsilon t will become e to the power, so epsilon t will should become e to the power epsilon 0. Suppose we start from very near to epsilon r t. Now you see, if we start from very nearer to n equal to 0, the population will increase exponentially. That means whenever we reaches towards the n equal to 0, it seems like that this point is repulse the populations, means it's just pushing away the population away from it. So this is called the repelling fixed point, or it is called the unstable fixed point. So that's how we know that whenever the state reaches towards the n equal to 0, it will cannot go towards n equal to 0, because whenever it will reach to n close to n equal to 0, the n equal to 0 will repulse and the population will increase exponentially. So that is why it is called the unstable fixed point, or repelling fixed point. Now let's see, is it the same case with n equal to k? Let's see. So n equal to, so suppose that this is n equal to k. Now suppose we are starting from very near here, epsilon. So now my nt is k plus epsilon. So Buzaji, are you following me, or if you have any question in this, means we will see these things elaborately in next classes, but I am showing a glimpse of linear stability analysis, how you can actually show the stability of the fixed points. Oh, okay, right. So nt is this. So if I put this n value in this is equation, so it will look like, so dk plus epsilon dt equal to r k plus epsilon 1 minus k plus epsilon ik. Now since k will not change with time, so this will d epsilon dt, since dk dt plus d epsilon dt, and dk dt will become 0, so this is d epsilon dt, so r, and so this is, okay, let me write it this way, 1 minus 1 means k by k minus epsilon by k, so this will go away, so r, and you see that k is much higher than epsilon, so we can neglect this term. So in the neighborhood of k, the equation will become d epsilon dt will become rk, and this is 1 minus 1 minus epsilon by k, so rk minus epsilon by k. So in the neighborhood of n equal to k, the distance between for k and current state of the population, that is epsilon, will look like minus r epsilon. So then if I solve this equation, it will look like epsilon t will become epsilon 0 e to the power minus r. Now you see the another interesting thing. If I start near to the n equal to k, the distance will, it says, it will decrease with time. Okay, it will decrease with time. So suppose this is t, this is epsilon 0 and this is epsilon. So you can see the distance of the current state of the population, that means epsilon, as time increasing, the distance between these and these two decreasing, because this epsilon will decrease. Epsilon will decrease means the distance will decrease. When the distance will decrease, that means the current state of the population is look like approaching towards n equal to k. Now since the population, as time goes, the population is increasing towards n equal to k, so this is not the same case, since this is e to the power minus rt, so this is not the same as n equal to 0. So n, when time goes on, n is approaching towards k, so it says that whenever the state of the population will somehow reach nearer to n equal to k state, it will uh, the distance between n equal to k and the current state will decrease as time increases. That means at some point of time, the population will reach n equal to k, and if it will reach n equal to k, the population will no longer change its state, and that means it will go to a fixed state, and that fixed state is attracting fixed point. So n equal to k is attracting fixed point. It is not repulsing, attracting fixed point, or it is called stable fixed point. Now we see that if we start from anywhere in the if my initial condition means initial population size is anywhere between 0 to k, my final state will always go closer to n equal to k, and it will always repelled by n equal to 0 state. So it will move away from extinction, and it will always go towards n equal to k. So that's how we can say the future state of the population will be n equal to k, and theoretically these will reach at n equal to k at infinite time, it required infinite times. But if you say practically, is there any populations where we can see this kind of growth? Now suppose that if you can recall from our previous classes, what means the population of the east, if I can go there, so this is the population of insects. So if you see from this Carl cell population of east 1993, this curve is exactly look like the curve that we are drawing here. This curve and the curve we have experimentally from observation we have seen from the east population in 1993. So we can say that population of east can be modeled through these continuous equations. So not only the population of east, so there are a lot of other populations that can also be modeled through this. So that are the population of bacteria yeast and protozoas, and there are other things also there which you can model populations of protozoa. So let me write it: bacteria, yeast, and protozoa. Protozoas. And another thing that water fleas, fruit flies, and Drosophila population of these things can be also modeled through our these equations. Uh, these equations. Now, for the clarity, I want to say that this linear stability is to show you only that where the future state means what will be the prediction from this equation. So if this is my predictor, so what will be the prediction that means what will be the final state of the populations, that I can say, at least we can say from linear stability analysis that the population will not go to extinct. It will grows to carrying capacity or something else, but we can safely say that if the population follows this type of equation, it will not go to extinction. And that is that. Now let's this is all about the continuous model. Now let's see discrete models. Now in the further in this course, we will only use the discrete model. So let me begin with let me introduce the discrete model first. Let me introduce the discrete model. Discrete model. Now Subhuja ji, as we have already discussed, so can you tell me what what type of populations can we model through discrete model? Means what type of property, means what kind of reproduction, if the population follows, then we can think that we can model the mathematize the size of the population through a discrete model. We have discussed it previously. Right, exactly, that's the correct thing. So if a population has a preferred breeding season, this is the correct statement, then you can see that then we cannot see the time as a continuously, because if I observe the population, because if I assume, means for simplicity let us assume that the individual will not die the in between two breeding seasons, means then what will you will see, means they can die, means there is a particular age of the death. So after breeding maybe they die, but in between two generation we will not see any fluctuation in the population. So that means if I observe the populations between first generation and the second generation, so from the first generation up to where the reproduction reproduction didn't happen, from that point of time you see the population will remain same, because no individuals will be further added in that populations, and we assume that no individuals is dying in the population, so we will see a constant number of individuals are there in the population. So in between the first generation and second generation, means after borning the second generation, so before borning the second generation we will see no change in the population. So that means, so the number of individuals that born at the that are the first generation individuals will remain same, and these n1 individual give birth some other individuals, so up to that point this will remain same. Now these individuals reproduce some other individuals, and that will suppose n1 number of individuals they reproduce, and then we will see n1 plus n equal to n2 at the next generation. Now in between these to these, means from birth to reach to their reproduction age, will see throughout in the population no change. So that means the population are not changing in a continuous manner, it is changing in a completely discrete manner. Then we can't write a continuous model, but we have to write we have to write something that that capture the growth rate of the population. So if I know that the growth rate means per capita growth rate of a continuous growth model is DNDT, so can you tell me what will be the equivalent of this in case of discrete populations, where my state is n1 in the first generation, and then in the second generation n2, in third generation n3. So can Subhaji tell you, means can you guess what should it look like? Okay, then okay, it's fine. Now we see what this DNDT tells us, that it is telling that change of number of individuals with time. So here in the continuous, in the discrete model, what is the change of individual with time? So in, suppose that will be n t plus 1 number of individuals are there in the t plus 1 generation. Now what was the number at the th generation? That is nt, and to what amount of time required for this? This is required 1 generation. So this is the rate of change of individuals per generation. So this is equivalent to that. Now into 1 by nt. So this is means the equivalent of the growth rate is n t plus 1 minus nt. What is the what is the increase in the number of individuals in the current generation t plus 1th generation from the tth generation by nt, that will be same as 1 by n dndt. Now is it clear? Okay, then first of all, so this will write. Now first of all, let's see the continuous, not continuous, let's see the unlimited unlimited growth model, growth or unlimited growth model, or what you say, the exponential growth, right? So now you can guess what should be, if I go with the similar logic as the continuous model. So what should be this rate of growth in t by n? Now you can Subhaji, can you guess what it should be? Nt plus 1, nt plus 1 minus nt by nt, that is the per capita growth rate for unlimited growth, or if there is unlimited resources available, what should be the per capita growth rate? Right, it should be r, it will become rnt later on, but per capita r is per individual's growth rate will be constant, because there are lot of resource they can use, whatever they did, means whatever they want they can use that resource, and if they using their resource, they will reproduce at a constant rate. So that means in case of here also, if you see here, in this case, okay, let me write it here, yeah. So here also the rate of change and 1 by n, so rate of change, dndt is rate of change, but per capita 1 by n dndt, what it is? It is r, per capita growth of the population is a constant. Now that's it. So dnt plus 1 minus nt equal to r. So then we can write it nt plus 1 minus nt Rnt. Maybe you are pointing toward these equations. So now this is nt plus 1 or nt plus nt. So this will by common nt 1 plus r. So now this is called the difference equations or map. This is called previous equation is called the differential equations. Now this equation is called difference equations. Difference equation, because the difference, the thing with we are dealing with is the difference of the population, current and the future generations population size. Now it is the predictor of the population, because why? Because it can predict the next generation number, next generation population size, if I only know the current generations population size. So that's how we write the discrete model for the unlimited resource. Did you get this point, Sobusaji? Then we can end, because it's past 12. So we can end this session here. Yeah. Hmm. Hmm. Huh. Hmm. Ah, no, you were right. You were right. But means there was a time window. So it is like 70s 66 to 1834. So there was a mathematician, or you can say population biologist, Thomas Malthus. Have maybe you heard this name, Thomas Malthus. So what he observed the growth of the population at that point of time from the past. Now what he observed, that population growth of human beings are looking like that it is growing exponentially. So for that, because at that point of time, means in 80s and 90s, 70s, and before that, there are a lot of resources available for human individuals. So it could be approximately at that point of time the human population was growing at an exponential rate. So you could think like that, but obviously, since the resource is limited, so whenever the population will grow, means a certain size, grow up to a certain size, then the population, the resource become limited, and the population will tends to saturate at a point. But it is true that human population was looking, if you observe the growth of the human populations, so that's why it is called Malthusian growth of the human population. So it is growing, it was growing exponentially. That was my answer. So right, yeah. Mm. Okay, so that is it. Okay, then see you in the next class, Monday. Okay.